So with the next presentation, we are leaving the railway system and also the Earth. We are going into the sky. Together with Drăgan, research scientist at Fraunhofer Institute for Cognitive Systems, and Akshat, Tandon, who is a quantum machine learning lead and AI researcher at Airbus Central Research and Technology. We are going to hear a presentation on quantum reinforcement learning for aerospace. I'm happy to have you two here with us. Please join me here on stage. And if you want to be recorded, it's better to stand here. If not, then you can stand over there. Here's the presenter. Stage is yours.
Thank you very much. Hello, everyone. It's been a great pleasure to be here to be part of this fascinating summit. Before we deep dive into what exactly is the use cases or problem statements for quantum reinforcement learning for aerospace sector, let me take a step or two back and give you a glimpse of what are exactly the problems in the aerospace sector, where we are actually thinking we could use QML as a whole, and what exactly are the typical activities related to quantum technologies inside Airbus, to just give you a glimpse before Theodora can continue with her experience on quantum reinforcement learning. So basically what we'll do is we'll explain you first the what and the why, and then basically we'll end up with how exactly to solve those problems. Could someone help? This is the middle one, right? Yeah? Okay, sorry. Thanks. Yeah. So just to introduce you, as you can see very clearly in this picture, this basically sums up very clearly our entire portfolio of what we do in Airbus. The small one over there is our A320 family aircraft, commercial aircraft. We also have defense products, so you can see something. The big aircraft at the left side of the image is basically a A400M military aircraft carrier, transport aircraft basically. And then at the top of it, you can actually see helicopters, and what you can't actually see in this image is basically our space products. So we have a lot of satellites as well as our products, and basically we are Europe's biggest satellite manufacturer. And of course, one of the critical challenge that we have as a collective overall is of course sustainability related, and that is also our motivation. So that's what you can see here. It is for us is to pioneer in sustainable aviation and aerospace for safe and united world. And we believe quantum technologies is one of those key technologies that should be fast-tracked to maturity to achieve these kind of targets for us. And thus, we are already very actively part of, we are actively engaged in being the early adapter for this technology. As you can see from our portfolio, we have a lot of products in different domains and different very diverse domains basically. So we of course have a very transversal application use case for quantum technologies. As you can see, we are working on one side on quantum communications. We are also on the other hand working on sensing, as well as we are working on quantum machine learning and optimization solutions, so quantum computing. But in this talk, we'll basically focus more on quantum computing as well as more specifically on quantum machine learning in that case. Of course, the biggest motivation for us to go into quantum technology is that because our problems, our problem use cases and scenarios basically require a lot of computational power in many cases. Engineers used to say before that aircraft is 10,000 parts flying in close formation, which is in today's, it's not just an aggregation of those moving parts, but it's also accompanied with a lot of sensors. So basically, we have aircrafts with more than 250K sensors, which of course have a lot of data which needs to be analyzed. Thus, to solve this challenge, we basically have our own HPC system, and we want to enable quantum computer or add quantum computer to that system as well, and thus provide better service and performances for our products and for our customers. So we also understand, like, because these problems and these challenges are unique, thus we also understand that the fastest way to achieve solutions for those problems is to work with the quantum computing community as a whole. And Airbus has already been doing that for years. And one of the example for that is some years back we launched Airbus Quantum Computing Challenge, where we introduced to contestant some really unique problems that are related to aviation and aerospace sector for us, for Airbus specifically. Now, because our company is also a company with European roots, so we are also very active in European ecosystem specifically. Equality is one of such project. Equality is European Commission project, which is also part of European Quantum Flagship project. Over here, we are working together with a lot of good partners to basically solve critical and strategic application use case related to aerospace and energy sector. So what are these then use case that we have basically? So we basically have divided our use cases in 4 different clusters. So what you can see over here is one cluster is quantum simulation, where we're dealing with quantum chemistry simulation use cases. The other one is quantum optimization, which is of course dealing with optimization related use cases for, like, for example, flight path optimization, etc. Then there's quantum solvers, which is dealing with use case similar to, let's say, CFD solvers, for which is one of the examples, for example. And then we have quantum machine learning, where we are trying to enhance the current classical machine learning algorithms using quantum solutions. So these are some of the projects that we have already been working on, and we have, in some cases, very promising results as well. Belonging to quantum optimization cluster, we did a project in collaboration with IonQ, which was basically focused on flight aircraft's load capacity optimization, so payload optimization. Thus, by achieving this optimized payload capacity, we could actually have more operational efficiency. With IonQ, we were also able to use or have access to their ARIA computer, quantum computer with 20 qubits. And what we try to do is basically we try to reduce the problem scale a little bit so that we could actually use their hardware in the end. Another optimization use case that belongs to quantum optimization cluster is powered by AQ, which is our Silicon Valley Innovation Center. And this was a project in collaboration with QBraid, where we are trying to accelerate software solutions by following approach by dividing a complex task into sub-modules, basically, of that task or subtask, and then tackling those subtasks or sub-modules with a quantum-inspired solution. Over here, the application use case and focus is flight trajectory optimization, where we want to optimize the trajectory in such a way that the fuel efficiency is highest, so thus making a flight more sustainable in that case. Now, because we're talking about sustainability, the other project which is also about sustainability is related to quantum simulation cluster, where we actually used quantum simulation to basically understand the chemical process behind fuel cell. Fuel cell is at the heart of our Zero-E project, and it's vital for to enable sustainable aviation. So thus, this project was in collaboration with BMW and Continuum, was really critical and vital to understand the processes involved in fuel cell, and thus to basically in the future have more efficient fuel cells basically developed by us. So this was one of the very critical projects and critical results. Now coming to quantum machine learning use case clusters, one of the use cases that we actually have worked on is anomaly detection in maritime situation. Of course, because of the heavy maritime traffic that we have nowadays, given high amount of vessels in the oceans, there's a need and a requirement to analyze abnormal behavior of those vessels, so to basically be able to predict when there is an let's say traffic accident or some kind of illegal activity happening in the ocean. So for this, because what we're talking about is a very massive data in real time, so for this we thought one of the solutions could be quantum solutions. So we in this case we targeted quantum enhanced neural network solutions, and typically we worked in this project with QCware, and what we with QCware we basically developed a quantum enhanced autoencoder solution that basically gave us really promising results in comparison to their classical counterpart. And on the right side, basically, you can see a typical general overview of how this the entire project was working. And on the left side, basically, is some example images of how a typical normal and abnormal images would actually look like in this case. Now coming to another use case related to quantum machine learning. We have another use case where we want to use basically reinforcement learning for a very efficient communication topology. In this use case, we basically want to use a quantum enhanced solution to be able to predict a topology which will basically enable an efficient and stable communication between flying aircrafts and ground station. So because we are talking about multiple agents or assets at this time, so basically the complexity also increases in this case. Thus, one of the possible solution could be quantum enhanced multi-agent reinforcement learning. Theodora in the next section would be talking about it more in detail, and will be also sharing her experience in quantum reinforcement learning and its relevance to this specific use case and to other use cases. But before I pass on to Theodora, that's it from my side. I hope that you get a clear understanding of that Airbus is actively involved in multiple use cases and multiple technologies to basically have to be an early adapter in this technology in the future. So thank you. I'd like to pass on to Theodora now.
Thank you. So I will start a bit with the motivation of why at Fraunhofer IKS we decided to start our journey with quantum reinforcement learning, and mainly is the fact that we live in the NISQ era. We are dealing with noisy intermediate scale quantum devices, which means we have limited access to devices with a limited number of qubits, which also means that there are not many results on real world data sets, and furthermore the results that are there are impacted by noise. And this is why our approach was to start with developing a hybrid quantum reinforcement learning algorithm that employs shallow quantum circuits, so it's applicable on these devices, and then to look into which architectures exactly to use and employ it on a well-established benchmarking reinforcement learning algorithm with the hope to gain an insight on how this works, which architectures are relevant, and eventually to be ready for the fault-tolerant large-scale quantum computing era. I will describe a bit the environment that we studied. It's a maze-like environment. It's called a frozen lake, namely the slippery frozen lake. We decided to take what seems like a trivial environment with 16 possible states. The agent can be in the start goal, in the end goal, or anywhere on the frozen tiles, and if it reaches the holes, the whole learning process finishes. And how we went to the next level was to say, okay, the lake is slippery, which means that at each time the agent wants to take an action, it has an 80% probability to take the action it wants, so to go up, down, left, or right, but there's also a 20% probability that it slips into the orthogonal directions of the ones it means. We decided to deal with this using a state-of-the-art algorithm, a policy gradient algorithm, namely the proximal policy optimization. And I won't go too much into detail, but we took the same algorithm, the same implementation that has already been benchmarked, and we replaced the normal function approximators, the ones that say which action is best to take from a certain state, and which reward do I expect, how good is a state, I mean, and replace those with neural networks, with quantum circuits. How we chose those quantum circuits was to find the ones that were justified by literature, but they all had a common architecture. They all had a basis embedding, so that the state of the agent, the integer from 0 to 16 that was displayed on the tiles before, could be embedded into a quantum state, into a quantum basis state. Afterwards, this input was passed to a trainable layer. We measured the output, and then to scale the output of the expectation values that we measured, we used linear layers. Then we tried 19 different quantum circuits with all with different types of entanglement, or most of them with different types of entanglement, linear, all-to-all, or circular entanglement, as well as shifting alternating blocks, as well as changing the entanglement gate. All of these were motivated by literature. For example, the biggest ones you see there, circuits 5 and 6, were firstly proposed as quantum variational autoencoders, with the latter circuits being used proposed actually for image classification. Our results were successful. In comparison to the classical solution, we chose a solution that employs neural networks of similar size in terms of number of trainable weights with the hybrid ones. To be more precise, even a little bit more, the neural network has over 100 trainable weights, whereas the parameterizable quantum circuits have less. And we noticed that, firstly, we reached more or less the same results. One should mention that these results are smoothed out. So while they do not seem to reach the reward threshold, they do. And apart from reaching the same reward, a comparable reward, if not even greater, what was more interesting is that the quantum circuits need less iterations, less interactions with the environment, which is important because not necessarily for this use case, but for other use cases, interactions with the environment may be expensive, so we are looking to minimize that. And this is why we looked into exactly what we wanted to see, what makes this better, and more importantly, how, if we could explain the difference in performances between these circuits. For example, in circuits in orange, red, and green here that you see, while they do seem to stabilize at more or less the same reward, this time to convergence is quite different, and we wanted to look into this. So we chose 3 metrics that characterize, firstly, in general, models. The normalized effective dimension can be used on any kind of statistical model to see how well this model can generalize. And then two more quantum metrics, namely the entanglement capability, which is self-explanatory. It shows how well the ability of a circuit to entangle states. And finally, the expressibility, which, looking at this nice formula, actually shows how well this circuit can generate all of the states included in the Hilbert space of random states. Nevertheless, when we try to plot this, to look at the metrics for each circuit and the results employed by the architecture that contains this circuit for both, the same kind of circuit for both the policy and the value function, we found no clear correlation. It was not easy to say that this metric can explain or predict some kind of results, even trying to group by entanglement gate, for example. And here you can see plotting the normalized effective dimension against the time to convergence, so against how many time steps until the learning process is stable. But the results were similar also for the entanglement capability and also for the expressibility. So in conclusion, our study employed 19 different circuits on a well-known reinforcement learning benchmarking environment. However, we did not find any kind of clear correlation between the metrics we employed and the successful results of the quantum circuits. So our next steps would be to look into other quantum metrics to see if those are relevant. Of course, to look into industrial real-world use cases and apply on those, like we were mentioning, our collaboration with Airbus. And finally, to look maybe into the impact of hyperparameters or anything else that can get us a better insight onto quantum reinforcement learning. And you are welcome to contact us. Here you have my LinkedIn and our Quantum Leads LinkedIn. And of course, you can visit our webpage if you want to look into other projects that we are into. Thank you.